All right, well, welcome to our final presentation of SC13 at the Nvidia GPU Technology Theater, sponsored by HP. We're glad to have Mark Harris here to tell us more about the new features in Cuda 6.
Thanks, Allison. Thanks, everybody, for coming this afternoon and staying for the very last talk. As Allison mentioned, I'm going to talk to you about what's new in Cuda 6. So I'm going to talk to you about 4 main features. There's, of course, many more features than this in Cuda 6. But I'm going to talk to you about unified memory, improvements to our libraries, GPUDirect RDMA and MPI. And if you were here for the previous talk from Professor Panda, then I'm sure he gave you much more information than I will. So, and then number 4, I'm going to talk about developer tools. So let's talk about unified memory. Today, in heterogeneous computing, you have 2 discrete processor types, and they each have their own physical memories. And so the programmer today sees exactly that. The programmer is responsible for allocating memory in both places and managing copies explicitly between those. What we're introducing with Cuda 6 is unified memory, which provides a unified managed memory space that spans the divide between the CPU and GPU. And the Cuda runtime handles automatically migrating data to the processor that needs to access it. So what that means for the programmer is dramatically simplified code. So here we have two programs. They both do the same thing. On the left is just CPU code, and it allocates data with malloc and then reads data from a file into the allocation, and then it sorts the file using qsort and then uses the data in some other way on the CPU before freeing the memory. With Cuda 6 and unified memory, the code to do this on the GPU would look something like this. Instead of using malloc, we just use Cuda malloc managed, and that gives us a single pointer that's accessible from either the CPU or the GPU. So then we can read directly into that Cuda, that managed pointer from a file, and then we can pass the same pointer to a GPU kernel. In this case, we have some hypothetical qsort that runs on the GPU, so we do a kernel launch for that. After we've sorted it, we can synchronize the device, and after that, we're able to use the data again on the CPU. So we access the same pointer again from the CPU, and then we free it using Cuda free. So unified memory delivers in 2 specific areas. One I've showed you is a simpler programming and memory model. You get a single pointer to your data that you can access from anywhere, and you don't have to do explicit memory copies. This greatly simplifies code porting, as I've shown, and especially if you have complex data structures. And I'll give you some examples of that next. The second area is performance through data locality. One way to do this that we had support for before would be to keep all the data on the CPU and then access it over a PCI Express from the GPU, and that gives you some of the benefits of unified memory, but very poor performance. So with unified memory, the runtime handles migrating data on a page level basis, so that when the GPU accesses it, it gets full bandwidth to its device memory. And the runtime guarantees global coherency at kernel launch and synchronization. Now, of course, you can still use everything that we have in Cuda today in terms of explicit memory copies for hand-tuning the performance of your code and for doing things like overlapping memory copies with computation. The programmer always has more information, or almost always has more information about the data access patterns of the program than the runtime or the compiler does. And so we still allow you to tune performance using those tools. So let me give you an example of how unified memory helps you port existing code and data structures to the GPU. So here we have a arbitrary struct that we've defined called data element, and it has some integer members, but it also has a pointer to string data. So here we have it in CPU memory where we've got a pointer to the string hello world. And so if we want to initialize that data on the CPU, but then we need to access it on the GPU, today that requires what's known as a deep copy. So it's called a deep copy because you have to copy the top level structure, but then you have to go deeper and copy the things that the data that's pointed to it, that it points to. And so this requires actually three copies. If we look at the code to do that in Cuda before Cuda 6, we want to launch the kernel accessing that data element. But in order to do that, we have to allocate space on the GPU for a copy of the element and for a copy of the string. Then we have to copy the element structure, we have to copy the string, and then we have to do a copy to make sure the pointer in the copy of the structure points to the GPU memory and not the CPU memory. So we have quite a bit of code just to launch the kernel and access that data. But with unified memory, we just use cuDMalloc manage to allocate the structure and the string in the managed memory space, and then either the GPU or the CPU can access it. So all we do is call the kernel, passing it the struct. So it's a big simplification. Another example, if we look at a linked list, which is a very common computer science data structure, today in Cuda, the only real option for that is to use zero copy or pinned system memory. And I mentioned this before, but the idea is that you allocate pinned system memory on the CPU and you keep your linked list there, and then the GPU would have to access it over PCI Express. And that's inefficient, but with a very complicated chain data structure like that, the code to update the linked list on the GPU every time would just be too much to make it worthwhile. So with unified memory, we can allocate one linked list data structure in the unified memory, and then since both the CPU and the GPU can access that linked list from the same pointers, we can pass list elements between the host and the device. We can create and destroy list elements from either place, as long as we make sure we don't have race conditions. And in the end, we're maintaining a single list rather than two copies of the list or one that we access slowly from the GPU. Unified memory really starts to shine when you look at it with C++. C++ allows you to overload the new and delete memory allocation operators. And what this means is that we can provide a utility class. Here I've defined this utility class called managed, which implements new and delete, and inside them it uses cuDMalloc managed and CUDA free. And once we've done that, we can then inherit from that as a base class, which means that it's going to use those implementations of new and delete in the subclass. In this case, you can see another change, and I didn't put all the details on the slide, but this is a string class rather than a char star, and I'm assuming that the string also has a copy constructor that uses cuDMalloc managed. And once we do those two things, then if we just on the CPU call new data element, then it's going to allocate the space in unified memory, which means that now that can be shared between the CPU and GPU. And not only that, but it allows us to pass it by value to the GPU kernel, which will cause the copy constructor to be invoked, and you'll get a copy made in unified memory. Or we can pass it by reference, and that's new in Cuda 6. You didn't used to be able to do reference parameters to kernels. So you can pass this data element by reference to the kernel, and no copy will be made. The kernel will just access it in unified memory. And all that just works automatically because we've used cuDMalloc managed inside of the new and delete operator and the copy constructor. The nice thing about unified memory in Cuda 6 is that it's just the beginning. We have a long roadmap planned for improvements to unified memory. Starting with Cuda 6, we have cuDMalloc managed, which gives you a single pointer to your data with no memcopy required, so that memcopy becomes an optimization rather than a requirement. And you get coherence at launch and sync. And this allows you to share complex C and C++ data structures between the CPU and the GPU. In the next releases of Cuda, we'll be adding optimizations to bring even more performance. For example, automatic prefetching of data when the runtime can see patterns in the way you're accessing memory, and also migration hints so that the programmer can help the runtime move data when the programmer knows it needs to be moved, or to choose specific page sizes, for example. I should have mentioned that in CUDA 6, unified memory is supported on 64-bit Linux, Windows 7 and 8, and so we'll be adding other OSs in future releases. Oh, and I should also say it requires Kepler, so CUDA compute capability 3.0 or later. So, for example, K10 and K20 GPUs are all supported. When we get to the next generation architecture called Maxwell, it adds a lot more functionality so that it allows us to unify the system allocator. So that means that you can use malloc, and then you can share basically any data between the CPU and GPU. And that means that not only is heap data unified, but also stack data. So you can have structures on the stack that then you pass to the GPU and things like that. And of course, Maxwell will have hardware acceleration for coherence, so it'll all be significantly faster. So that's unified memory. The next feature of CUDA 6 that I'll talk about is what we call the XT library interface and drop-in libraries. XT stands for extended, so this refers to new features in cuFFT and cuBLAS level 3 that provide automatic scaling to more than one GPU per node. And it also provides out-of-core operation for BLAS level 3 operations like large matrix-matrix multiplies. The BLAS 3 interface is a host interface, which means that you pass it pointers to CPU memory. And so it tiles up the matrices and automatically overlaps transfers between the CPU with computation on the matrix. In cuFFT, we support single and batched transforms across up to 2 GPUs in CUDA 6. We may support more in the future. And today, this is tuned for our multi-GPU cards especially. So we get very good performance on K10, which has 2 GPUs. So you can see you get a bit of scaling with 256 cubed transforms, but 512 cube transforms get quite good scaling. Again, cuBLAS provides a host interface that provides not just multi-GPU scaling, but also out-of-core operation. So that means you can do matrices that don't fit in the memory of your GPU. This is all configurable. I mean, the matrix sizes that and how it scales and what GPUs you use is all configurable. This is limited to level 3 routines. Of course, the level 1 and level 2 routines tend to be bandwidth bound, so it doesn't make as much sense to try to scale those to multiple GPUs. The graph here shows 1 K20C on the bottom and 2 on the top, and of course you get about twice the performance on 2. And this line here shows the out-of-core or the in-core limit. So once we go past this line, the matrices are no longer fitting inside the memory of one GPU, and so it just continues to perform after that. In addition to multi-GPU cuBLAS, we're providing a new library called NVBLAS, which is a drop-in replacement for CPU-only BLAS. So you can automatically route calls from your application to standard BLAS 3 interfaces to cuBLAS. You can optionally configure how this happens, so you can configure what matrix sizes will be offloaded, the tile size to use, and which GPUs in your system to use, for example. And you can also specify what CPU-only BLAS library you want to use for operations that are not offloaded to cuBLAS. So to use this, there are 2 ways to do it. You can either, if you're able to relink the application, you can specify libNVBLAS before your CPU BLAS, for example MKL, in the link line, or you can, on Linux, you can use LD preload to load the dynamic library libnvblas.so before you run your application. And so an example of that, here we've used NVBLAS with R. So the statistics package, and what I've done here is LD preload, and I pass it the path to libnvblas running R, and then there's 3 lines of R code that just create 2 random large matrices and then multiply them and time that. And then we've produced a graph of that here, and this is scaling up to 4 K20X GPUs. So you can do this in any application that uses standard BLAS 3 interfaces. So for example, Octave or Scilab, etc. Number 3 is GPUDirect RDMA and MPI. So we announced GPUDirect RDMA in Cuda 5. What it is the ability for to transfer data from a GPU on one node across an InfiniBand network to another to a GPU in another node without going through the host on either side. And so what that does is it dramatically reduces the latency inside the node, and the result is better MPI application scaling, as shown on the right. So here you can see we have a 62% reduction in GPU to GPU latency, and then better MPI scaling. This is available, or when when Cuda 6 releases, this will be available in NVBLAS 2 and OpenMPI on top of the Mellanox OFED stack. And if you'd like to see a demo of this before they shut down, visit the Mellanox booth. So last but not least are developer tools. Tools are crucial to enabling developers to use our platform, and so we're continuing to invest heavily in this area. So I'm going to tell you about several new features. A big one is support for remote development inside Eclipse Edition and also in the Nvidia Visual Profiler. This enables you to have a local integrated development environment, say running on your laptop, for example, or on your desktop machine that doesn't have a GPU, and then to run your GPU accelerated application remotely on, say, a cluster node or a server with the GPU that you want to run on. The IDE takes care of automatically syncing. So if you build your app and then it syncs the bits over and then runs them, and so you have access to the full debugging and profiling capabilities of the IDE. This also supports cross-compilation to ARM if you happen to be running, say, on a Kayla development board or something that has an ARM CPU. In Cuda 5.5, we released something called MPS, which stands for Multi-Process Server. MPS provides the ability to run multiple MPI ranks on a single GPU. So if you imagine you have an application, an MPI application, and each rank launches kernels, Cuda kernels, but perhaps the size of the amount of parallelism in each kernel is not enough to fill a single large Kepler GPU. This enables you to run multiple MPI ranks concurrently, and their kernels will run at the same time on the GPU. With Cuda 6, we're enabling tool use on the MPS programs so that you can profile MPI apps that are using MPS using NVProf, our command line profiler, and then you can import the data from those runs into the visual profiler, and you can visualize multi-process timelines like this inside of the NVIDIA Visual Profiler. We also now enable running MPS applications inside of Cuda memcheck, which helps you find memory errors such as out-of-bounds accesses, as well as race conditions, such as forgetting to synchronize threads and things like that. And then the last feature I'm going to talk about is improvements to our guided analysis features in the Visual Profiler and the Nsight Eclipse Edition that provide more detailed kernel profiling. So the profiler is now able to count instructions, and so it can show you lines of code where your program spends the most time. So for example, here we have this line of code that does a fairly complicated operation with a bunch of memory lookups, and that executes 9.7 million instructions across all the threads. And here you can look inside that and see the corresponding assembly code if you want to look at the details of the assembly. In addition to this, in addition to the hotspots, the profiler also shows you these bar graphs on each of the significant code lines. And what that shows is the amount of divergence. So divergence is where some threads execute the line of code and some don't. And so up here you see a little bit of blue. It's a little bar graph, and it shows that there's a small amount of divergence where some of the threads did not execute that line of code, perhaps because they exited the loop earlier than other threads. And that can help you find problems where maybe you need to refactor your computation to have more coherence or something like that. The visual profiler also gives you a much more detailed instruction mix visualization for each kernel. So here for a single kernel, I can see how the instructions break down. So floating point, integer, control flow, memory access, etc. And then within that, I have an inset here that shows the floating point composition of instructions for adds, multiplies, multiply adds, and special instructions. And that helps you get a big picture view of how your kernel is utilizing the functional units on the machine. So that's it for my overview of CUDA 6. I hope I've shown you how some of the ways that it makes parallel programming easier, especially unified memory. If you are interested in getting early access to CUDA 6, we'll have a release candidate, and you can be notified of that release candidate and have early access to it if you sign up for our CUDA Registered Developer Program. That program has other benefits, such as access to some other early access programs and the ability to file bugs directly and things like that. So I think I have time for questions.
You certainly do, Mark.
Yeah. Gautam.
Is CUDA 6 the support only beyond K20, not for, say, Tesla series isn't supported on this, or is it backward compatible?
So CUDA 6 supports all GPUs, all NVIDIA GPUs, but unified memory specifically only works on compute capability 3.0 and higher, which means the GK104 based products like K10 and K20 and K40 and beyond. So, yeah, James?
Yeah, Mark. Okay, so this is probably two aspects of the one question, but can you, with the unified memory model, does it support multiple devices per node?
Yes, the unified memory supports multiple devices per node. The devices need to be P2P compatible. So if you have two of the same device, then that's fine. If you have two different devices and they don't support peer-to-peer transfers, then it will fall back to using pinned host memory. And so you'll see that your accesses will be slower.
Yeah.
So.
Cool. And also, can you say anything about the coherency algorithms you're using, particularly in that kind of situation?
So right now it's software coherence. So the coherence points are at kernel launch and at device synchronize. So either CUDA device synchronize, or if you're only using one stream, you could synchronize that stream, or use an event synchronize. It basically is keeping track. It's moving pages, and keeping track of dirty pages, and then synchronizing those at those sync points. Yeah.
In other words, if you get it wrong, you could pay a fairly solid execution penalty if you're trying to write to the same data structure.
Can you just say that again?
No, I was just so you could pay a serious penalty if you're trying to write to the same data structure with two kernels on different devices, or if you
yeah, well, you could have a race condition in that case.
Yeah.
If today in CUDA 6, what we do to prevent that between the CPU and GPU is if you forget to do device synchronize after the kernel, then of course that's an asynchronous kernel launch. If you then immediately access that same pointer from the CPU, then you'll get a seg fault because they're accessing at the same time, and we don't support the coherence at that fine a granularity.
All right, thank you.
Yep.
Any other questions for Mark?
So is this the right understanding that all the memory accesses are translated into explicit memory copy by CUDA compiler?
No. When the CPU is able to page fault. So when the CPU accesses data allocated with CUDA malloc managed, then individual pages will be moved when the page faults occur. When the GPU accesses the data, basically the allocation is synchronized so that we know that all the data is there on the GPU before the kernel launches, and so it's not the same. It's not the same as transferring the whole allocation every time. It's just the parts that need to be updated.
Any other questions? I gather not. All right. Well,
Okay.
thank you again, Mark.
Thank you. Thanks for coming.
Thank you.
Thanks for staying late.
Yeah, thank you to everybody for attending the NVIDIA GPU Technology Theater over these last few days at SC13. Once again, everything that was in the theater over these 3 days has been recorded and is available online or will be available online tomorrow morning, the full set of speakers, slides, as well as videos. So once again, thank you. Check out NVIDIA.com, our GTC conference in March. If you like the content here at SC13, there's 400 sessions of similar content in San Jose in March. Once again, thank you. See you next year at SC14 in New Orleans.